the videos you upload are still like too blur.
I know.
Too blur.
Like too
blurrier than the iPad quality.
It's like 240.
I think if I
the
do it,
resolution is like 240.
240p.
Oh, that's not enough.
if you're following along with this though from the school G, I think you'd be able to see everything. I'm hoping. I know it is a lower quality video, but man, it uploads so fast. If I do the high quality, my gosh, it takes like 15 minutes to upload a third of a lesson.
Why do you have to split it up?
That's what I read there.
Play a game of pickup basketball.
Yeah, that's not a bad idea. I could use that.
All
right,
no, write some more bars.
So anyway, yeah, we. Now I think I mentioned this yesterday. When I'm doing Hess's Law, my strategy is to try to just arrange these given equations so that I get my reactants with the right coefficient. The target reaction has sodium bicarbonate. I see sodium bicarbonate one time in the givens, and that's right there. So I've got to turn that first reaction around. And then yields the what the original reactants were. Now, the delta H of this reaction, because I turned this around, would be negative of that, which is going to wind up being positive 16.9. So, if I just now get rid of that, add these two together, the HCO3s will cancel out, and I'll get the equation that I'm hoping for. And the delta H of this equation is positive 28.7. If 1 mole of baking soda dissolves in acid, then it would take in 28.7 kilojoules. If you had this compound, that's baking soda, in the freezer bag lab, you would have felt it get cold. It's taking energy from the surroundings. If you put your hand on there, your hand now is giving energy to it, and it'll feel cold. We're not going to do it, but would you be able to determine the delta H of this reaction, not with this information, but with the heat of formation table in the book?
Yeah.
Not the bond energy table. That you'd have to be able to draw the Lewis dot structure of that. We're not there yet in this class. But using the heat of formation table, you take that plus that from the book and subtract that, and then you could find the delta H. It would be very close to 28.7, if not the same. Now, and I don't think we're going to do this part either, but how much heat is released or absorbed when 4.2 grams of sodium hydrogen carbonate reacts? Because we have this for our delta H, this implies that is the amount of energy that would be taken in by 1 mole of baking soda. Do you agree that's per mole of baking soda? Why? Because the coefficient there is a 1. Yeah. If it were a 2, I would have had to multiply this thing through by 2, right? And we would have wound up doubling the delta H. So this is a conversion factor that you can use as a stoichiometry step. We would just do this. We could go 4.2 grams of baking soda. Change to moles. 84 grams in a mole. And then that next step, now that we have moles of baking soda, now we use that standard delta H of the reaction. It would be positive 28.7 kilojoules in 1 mole. So you're going to encounter questions like this, where you have to do stoichiometry that includes thermochemistry data. So this will wrap up all the theoretical delta H business. Now let's talk experimental. We all good? To talk experimental determination of delta H, we need to establish something, and this is weird to me. We have the first law, there's also a second and a third law of thermodynamics, and then scientists decided that there should be like a law that comes before the first. I think this is pretty equivalent to the first law of thermodynamics, but apparently physicists don't. So here we have, before the first law, we have the zeroth law.
Oh, zero.
Yeah.
The negative first law.
Yeah, that's the next step. Yeah.
No,
No,
there
no,
isn't.
that would be the
Oh
next
my
one.
God.
Though. If there was something that was like a foundation of this law. The two objects are at different temperatures. If they're put together, one is going to transfer energy to the other until they reach this wonderful idea of thermal equilibrium.
What you say? No, you're not.
Zeroth law. I just hate that. You could have given it a different name and not use a number for it.
Let's call it the Zeroth Law.
Wait,
Yeah,
wait, what? What difference does that make?
It's not zero with
Zeroth.
Zeroth. You pronounce it wrong.
Hero.
Like Xerox. Xerox.
Is that even like an illegit word like
Zero.
It is, yeah. In fact, I had to go and look up how to spell it. I didn't know if it should be ETH or just ZEROTH. And this is what book has.
Zero with law.
All right. The first day of this chapter, I showed you a picture of an egg in a frying pan. And let's consider that for a moment. We've got a frying pan that's very, very hot. And it really has nothing to transfer heat to, so it just can like transfer it to the environment. But assuming that there's no heat loss, so we've got this very, very hot frying pan. Assume that the heat control of the frying pan is turned off. So as soon as you turn the heat off, it still is very hot. Drop an egg onto that thing. What's going to happen to the temperature of the egg? It's going to increase. So it starts low and it starts to go up. In fact, it goes up very quickly if it's a hot frying pan. What happens to the temperature of the frying pan?
Decrease.
It is going to decrease. Why?
Because the heat from it is
It's giving some of its heat to the egg. So the pan goes like this, the egg goes like this, and so the pan continues to lose heat, and the egg continues to gain heat, and the egg warms up, and then eventually they get to the same temperature. Is that the halfway mark between the initial temperature of the egg and the initial temperature of the pan? They go the same distance? No.
Maybe if you don't.
That amount that the temperature is changing depends on two things.
Did you continue heating?
Yeah, we've turned it off, so it's not continuing to be heated. It's just a very hot.
Environment.
Not volume. The
Surrounding.
mass. The mass dictates. Like the pan is much heavier than the egg, so the pan is going to cool off slower than the egg goes up. There's another thing, property. Yes?
Surface area?
No, it's not surface area.
It's,
Volume.
No, it's like the endurance
Not
for
volume.
heat. Like
And-
water has this like really high.
That's what I'm talking about. There's a property of matter that determines how much energy you need to add to it to get it to warm up or cool off. Anybody remember what the name of that property is?
Thermal endurance. No.
What's that? Specific heat capacity. The specific heat. The specific heat. So I'm thinking that the metal is going to have lower specific heat than the egg does. However, the metal is much heavier. So the metal is going to lose heat at a certain rate. The egg is going to gain heat at a certain rate. And they change temperature. Eventually, they'll get to the same final temperature, which is not the same difference for both. The egg's probably going to rise more than the pan went down. That's the idea of thermal equilibrium. As soon as they're at the same temperature, there's no more transfer of heat. The pan is no longer giving heat to the egg. Is there any point at which the egg is warmer than the pan? No, the only way that the egg can be warmer than the pan is for the egg to start with more energy because, yeah, the egg is warming up as a result of the pan going down. And they're going to just stop right there. Thermal equilibrium. Yeah.
Do they like stop transferring energy, or it's like a certain energy? It's like,
Yeah, because of the differences in specific heat, eventually they'll start to cool off because they'll be losing energy to the environment. And the egg being lighter is probably going to lose more energy. And then as soon as the egg cools down a little bit faster than the pan now has more energy. The pan's going to give energy to the egg, and they'll come back up. So there will be kind of that difference the whole time. If you're watching this on the computer, yeah, what you hear there is they're talking constantly, so I apologize for that.
Hello.
Yeah. All right. Now, I do have part of this that I want to just cover up. You remember this expression. The C that's in the middle of that, that is the specific heat. For water, what's the value for water? Specific heat of water.
4.18.
That's right.
Yeah.
Unit, Siddharth?
Joule.
Joules per gram degree Celsius.
Oh, I got.
How much heat, that's the joules, does it take to raise 1 gram of the substance by 1 degree Celsius? That's a property. That's for water. Only for water. Every substance has its own specific heat. In fact, ice is different from 4.18, and steam is different from 4.18. And they're different from each other. What are you saying?
What is that for ice?
2.1.
there should a steam be like
It's 2.16, Girish. 2.16.
He remembers the 6 in it.
Oh wait.
Now, I joke about the low budget aspect of the calorimetry that we do here because we just use plastic cups, styrofoam cups. The equipment that you might use at university, like when you go to U of M and you have to do a calorimetry lab, you're probably going to use these fancy calorimeters. And I'll bet the fancy calorimeter, what's in the middle of it? Styrofoam. So we're just cutting out. You're probably using like $50 equipment, and we go to the dollar store and buy enough for a whole class with $1. I'd like to do a calorimetry experiment with you this morning. But let's just go ahead and do that right now. This relationship right here, this is what the law of the Zeroth Law of Thermodynamics, also known as the law of conservation of energy. That's what that says. When I have a change going on in water, like the experiment that I have to do with you today, you're going to put something into water and it's going to dissolve. Turns out to be an endothermic reaction. So the water is going to be giving heat to that substance in order to help it dissolve because it's endothermic. So if we're monitoring the temperature of the water with a thermometer, what are we going to see the thermometer doing? It's going to go down because the water is giving heat away to this process which allows it to dissolve. All right. Now here's what I have. We know that Q equals MC delta T. We're using that, and I'm going to take you back to around slide number 10. And that's too far, sorry.
Yeah, I see it.